Okay, let's unpack this. For anyone working deeply with sequence modeling, and I mean, whether you're building foundational models or tackling these extreme time series, the context window limitation of standard transformers, that brutal quadratic O of n squared time and memory complexity, is just the scalability problem that never goes away.
It's the perennial bottleneck.
Exactly. So today we're doing a deep dive into a paper that offers a really compelling way out. Titans, learning to memorize at test time.
This is a radical piece of research. The source material from the Arxiv preprint details an architectural approach that it fundamentally redefines how we think about memory in these models.
So our mission today is what?
Well, our mission is to professionally and comprehensively outline how Titans manage to scale to context windows larger than 2 million tokens. Not just scale, but do it while maintaining superior accuracy against, the state-of-the-art linear recurrent models and even some of these huge transformer baselines.
The conceptual framework here is what immediately grabbed my attention. The authors ground their work in neuropsychology. They view the standard attention mechanism as a kind of short-term memory.
Right. It's highly accurate for local stuff, but contextually limited.
And then they introduce this novel component, a deep neural module, that acts as a long-term, more persistent memory. It's such a clean analogy for a really complex technical problem.
It creates a powerful mental model. And to understand why this is so necessary, we have to start with the fundamental trade-off we're all facing.
The ON2 problem.
Exactly. Pure transformers, as you said, model dependencies beautifully, but that O of n squared complexity makes them impossible to scale for huge sequences. It just cripples applications like truly long-term time series forecasting or, analyzing massive multi-document contexts.
So the industry pivoted to ON solutions, the linear models. We saw linear transformers, and now these increasingly popular linear recurrent models, which solved the complexity issue. They gave us speed.
But we immediately ran into what you might call the compression crisis.
You trade efficiency for expressiveness.
Precisely. The core problem is that these long contexts cannot be properly compressed into a fixed-size vector or matrix-valued hidden state. That fixed state just becomes a severe bottleneck.
It can't hold all the detail.
It just can't. Not for complex reasoning over millions of tokens. And this points to a conceptual gap. None of the current major architectures, LSTMs, transformers, Mamba, they don't truly emulate the specialized interconnected memory systems we see in human cognition, which can actively learn and memorize the abstraction of past history.
That's a great point. And if we frame the existing models through that memory lens, the gap becomes so clear. RNNs try to compress everything into that single vector state.
Right. And transformers avoid that compression by holding on to all the key value pairs, but then they're just limited by the physical size of the context window.
So the Titans paper really starts by asking these foundational architectural questions about how to design a better memory system.
Those questions are crucial. What is a good memory structure? How should it update? How is information retrieved? And then the big ones, Q4 and Q5, which emphasize the need for interconnected and, importantly, deep memory modules.
And their answer to all of this is the Neural Long-Term Memory Module, or LMM.
The LMM, the heart of the paper.
So let's dive into it. This is not a static lookup table or some simple cache. The authors frame the LMM as a deep neural network, specifically simple MLPs with one or more layers that learns how to memorize and store data abstraction.
It's essentially a meta-in-context learning model that trains online at test time.
That phrase, at test time, is key. So this memory module is constantly updating its own parameters as it processes new input.
Yes, and how it decides what to store is just brilliant. It borrows an idea from human memory. We tend to remember events that violate our expectations, things that are surprising.
So, okay, how do you translate surprise into a functional metric inside a neural network?
In the LMM, surprise is measured by the magnitude of the gradient of the associative memory loss function with respect to the input. If some new data, X, generates a large gradient, it means the current memory state was a poor predictor. It was surprised.
And so the memory needs a big update.
Exactly. A high degree of surprise means a significant update is needed.
Wait a second. If surprise is just the momentary gradient, wouldn't one massive surprise, say, a huge topic shift in a document, wouldn't that risk memory failure by causing all the subsequent gradients to become too small to matter? How do they handle that instability?
That's a very sharp point. And that potential instability is precisely why they introduced the momentum-based update rule. They realize the momentary gradient just isn't enough.
So they break surprise into two components.
Two components, past surprise and momentary surprise. The memory update is based on this term, SAINT. where saint equals atat times st1 minus the tat times the gradient.
Okay, let's break that down for the listener. The saint term, that's like the momentum in standard optimization.
Absolutely. It's a memory of surprise aggregated over time. And the terms atat and thetat are the data-dependent gating mechanisms.
So they're adaptive.
They're adaptive. ATAT controls the decay rate of past surprise, how quickly you forget previous shocks. And THAT controls how much of the momentary surprise you incorporate. Because they depend on the input token, the model can adaptively decide whether to integrate the new shock or let the past surprise guide the update. It's all based on context.
And the loss function driving all this is pure associative memory, right? Just learning the mapping between keys and values.
Yes. The objective is to learn strong associations at test time. And this internal learning loop, the meta-learning, is totally distinct from the outer loop where the whole architecture is trained. That's crucial for its expressivity.
So we have a mechanism for learning driven by surprise and momentum. But for documents up to 10 million tokens, you can't just accumulate knowledge forever. Forgetting becomes critical.
That's where the ingenious weight decay mechanism comes in. They incorporate adaptive forgetting directly. MT equals 1 minus alpha times MT1 plus same day. That alpha is the adaptive forgetting gate.
So by applying weight decay, they're ensuring that unused or less relevant parts of the memory just naturally fade over time.
Right. And the paper highlights that this formulation actually generalizes the gating and forgetting mechanism you find in modern recurrent models like Mamba 2. So it is a strong theoretical grounding.
And once the memory is updated, retrieval is simple, just a forward pass of the trained LMM without any more weight updates.
Exactly. M star of QT. Simple as that.
Okay, the theory is compelling, but in the real world, running this deep sequential LMM update for every single token would just kill performance on modern hardware. It would neutralize the whole ON efficiency gain.
Right.
So how do they actually parallelize this beast? It's fundamentally a linear recurrence.
This is the implementation breakthrough. While it's theoretically ON FLOPs, you need tensorization, you need matrix multiplications or mapmuls to really leverage GPUs.
And the problem is the sequential nature of that momentum term, saint. You can't calculate saint without knowing saint 1.
Correct. The solution was to split the sequence into small chunks and then reformulate the entire complex update gradient descent, momentum weight decay using mapmuls and sums. And most critically, they realized that within a chunk, that momentum term is a linear recurrence.
And because of that structure?
Because of that structure, they could apply the parallel associative scan technique.
Okay, can you quickly outline what that is for our listeners? Why does that make the difference here?
Sure. Associative scan is a technique designed to take mathematically sequential operations and rephrase them into a set of parallel matrix operations. Imagine computing a running total. You normally need the previous sum. Associative scan uses the property of associativity to pre-calculate intermediate results in parallel.
So they transform what looks like a sequential token-by-token update
Into a parallel batch calculation, which is exactly what modern GPU tensor cores are built to do.
That's the key to making this expressive deep memory module actually competitive on a hardware level. Brilliant.
And with that functional LMM, they didn't stop there. They recognized the memory needs context, which led to the full Titans architecture family.
But before we get to the variants, we have to mention the persistent memory.
Yes, the persistent memory, or P. This is a non-contextual module. It's a set of fixed, input-independent, learnable parameters that are just appended to the start of the sequence.
So P is essentially a task instruction manual, or a meta-memory. It helps stabilize the model and mitigates that inherent causal attention bias that tends to overfocus on the first few tokens.
Precisely. It gives the model a reference point. And incorporating the LMM and P leads to the three core variants of Titans.
First up is memory as a context, or MAC. In this design, the LMM retrieves historical context, and this is concatenated with the persistent memory in the current segment. Then standard attention just processes that whole block.
It's incredibly efficient. The short-term attention can actively decide if it needs to query the long-term memory or if the local context is enough. It helps the LMM focus on storing only the most critical abstract information.
Then there's memory as a gate, or MAG. This uses sliding window attention for the short-term part and the LMM for long-term, and their outputs are combined with a nonlinear gate.
And finally, memory as a layer, or ML, which is the most traditional hybrid approach, just stacking the LMM and SWO sequentially. But as the authors point out, this limits the model's power to the expressiveness of each individual layer.
Which brings us to the theory. The paper has a key theorem showing that because of this expressive, deep, data-dependent LMM, the Titans family is theoretically capable of solving problems beyond the complexity class TC0.
That's a profound statement. TC0 is what limits models like pure transformers and diagonal linear recurrent models. Proving that Titans can transcend this class gives strong theoretical backing that this specific memory structure, this deep, nonlinear, momentum-driven update, gives the model capabilities that others just cannot achieve over extreme lengths.
And the empirical validation really backs up the theory. Starting with standard language modeling and reasoning, the results showed Titan's variants just consistently outperform modern recurrent models, like Mamba and DeltaNet.
And what's really striking is that the standalone LMM, with no traditional attention component, outperforms all the non-hybrid baselines, including Transformer plus Day.
That's not a small finding.
No, it validates the LMM design itself, the surprise, the momentum, the nonlinear structure, as a fundamentally superior mechanism for contextual abstraction.
And the ultimate test for pure context length is the needle-in-a-haystack evaluation, right? Up to 16K sequence length.
Here, the LMM and all the Titans variants show superior performance and, crucially, consistent stability. They don't suffer that severe performance drop you see in models like Mamba 2 as the length increases.
That stability has to be the adaptive forgetting mechanism, the weight decay.
Absolutely. It prevents the memory from getting saturated or polluted, which is what causes other models to crash when you push their context limits.
But the truly breathtaking results for me came from the extreme long context tasks, specifically Babylon, testing reasoning across sequences up to 10 million tokens.
A million tokens. The scaling here is revolutionary. In the fine-tuning setup, Titans, MACFT, despite being a much smaller model, showed superior performance.
And it didn't just scale, it actually outperformed huge commercial models, including GPT-4, GPT-4o Mini, and Llama 3.170B on that task.
Right. It's proof that architectural innovation in memory can eclipse brute force parameter scaling when you're dealing with extreme context.
And this power isn't just restricted to language. The paper showed impressive domain generality. Let's talk time series forecasting.
Yes, they replaced Mamba with the LMM in the Simba framework and got the lowest MSE and MAE across all the big long-term forecasting benchmarks. The memory module is robust for numerical and temporal data.
And for DNA modeling, Titans were competitive with state-of-the-art architectures like Hyena DNA. The LMM seems universally effective.
It speaks to the generality of the mechanism. Memory abstraction, driven by surprise, is valuable whether the data is text, time, or the genome sequence.
Let's synthesize the internal workings a bit. Looking at the ablation studies, what did they learn about the memory depth? Does a deeper LMM always mean better performance?
The paper confirms that deeper LMMs, so 3 or 4 layers, do achieve better perplexity and greater robustness, particularly at that 32K context length. But there's a clear and expected efficiency trade-off.
More depth, less speed.
Exactly. Deeper memory modules show a linear relationship with reduced training throughput. You gain robustness, but you lose some speed.
And how does the overall efficiency compare to the existing linear models?
The LMM standalone is slightly slower than, say, Mamba 2, which is the direct consequence of its deeper, more expressive process. But interestingly, the hybrid Titans variants, especially MAL, were often faster than the baselines because they could leverage highly optimized kernels like slash attention for their sliding window component.
And finally, looking at the LMM's internal components, which design choices provided the biggest performance lift?
The ablation study confirmed that all components contribute positively. But the greatest performance gains came from, in descending order, weight decay, that adaptive forgetting, then momentum, then convolution, and finally the persistent memory. And architecturally, MA and MAG were consistently better than the stacked ML design, with MA proving to be the best choice for those ultra-long context tasks.
So what does this all mean for you, the listener? The Titans paper establishes a highly effective, theoretically expressive architecture that successfully overcomes the long context limitations of transformers. By designing the LMM, this online learning neural long-term memory module, they've created a system that efficiently stores knowledge abstraction.
And when you couple it intelligently with attention, like in the MAC variant, it achieves state-of-the-art results across incredibly diverse domains, scaling up to millions of tokens without compromising accuracy.
It's a landmark paper.
It really is, and the core tension identified in the ablations is that trade-off. Deep LMMs are better, but they're slower. This raises a really important question for future research, building on their parallelization success. How far can we push the efficiency versus expressiveness trade-off by making the adaptive parameters the forgetting rate, the surprise incorporation, the momentum decay functions of the input chunk rather than the individual token. And what are the theoretical limits on the expressivity loss if we introduce that level of chunk-wise approximation?